B3, we're asked to compute the tan of arcsine of x for x between -1 and 1. So the first thing that I'm going to do is I'm going to draw what arcsine of x does in terms of output angles. So arcsine x equals theta implies that sine of theta equals x, which equals x over 1, which is opposite over hypotenuse. So in my interval here, I'm going to have my two possible triangles. I have x and 1. And now when I'm negative, it's the x goes down here, which is negative, and 1. And in both cases, I get √1 minus x squared. So these are my two triangles. Okay? And now if I take tan of these two triangles, in both cases, tan of theta will equal x over √1 minus x squared. So for both the upper triangle and the lower triangle, tan of theta will equal x over √1 minus x squared. And this is when x does not equal 1 or -1. Otherwise, tan of theta does not exist. So tan of arc sine of x equals x over √1 minus x squared if -1 is strictly less than x, which is strictly less than 1, or undefined when x equals 1 or -1. Here we have a split point technique for inequality. And this one's a little bit more challenging than what we've seen before because we have this ln. So here we have ln of x plus x squared minus 3x over x squared minus 3x plus 1 minus x squared plus, or minus 1 is greater than 0, which implies that ln of x plus x squared minus 3x over x squared minus 3x plus 1 minus x squared minus 3x plus 1 over x squared minus 3x plus 1 is greater than 0, which implies that ln of x minus 1 over x squared minus 3x plus 1 is greater than 0. And now I have to figure out what my critical points are. Now, or my split points are. My split points are when the numerator or the denominator equals 0. And I'm also going to add ln of x cannot implies that x is greater than 0. So I have this added piece of x being greater than 0, but let's suppose ln of x minus 1 equals 0. Well, this implies that ln of x equals 1, which implies that e to the ln of x equals e to the 1, which implies that x equals e. So that's one of my points. And now I have x squared minus 3x plus 1 equals 0. And here, I want to multiply to 1 and add to √3 over 2. I'm just going to go straight to the quadratic formula. 3 plus or minus the root of 3 squared minus 4 over 2 equals 3 plus or minus √5 all over 2. So x equals plus or minus, or x equals 3 plus root 5 over 2 or 3 minus root 5 over 2. So I've got my 3 split points, and I have to be greater than 0. And here, 3 minus root 5 is less than 3, so I am happy. Okay. So now, or root 5 is less than 3, so this is going to be positive. So now I create my split points. Okay. Now here, these numbers are ugly enough that I really wouldn't put them on a test. X minus 3 plus root 5 over 2x plus 3 x minus 3 minus root 5 over 2. As I said, I wouldn't put these ugly numbers on a test. I'd make it nicer, but we can do the same approach with our ugly numbers. And now I'm going to add one more point. My 0, my 3 minus root 5 over 2. And then I have e and 3 plus root 5 over 2. And here, I don't even know what's bigger, e or 3 plus root 5. This is something, because I have to look it up right now, it's absolutely not something I would put on a test. 3 plus square root 5 divided by 2. That is actually less than e. So because this is less than e, my order is going to be 3 minus root 5 over 2, 3 plus root 5 over 2, and e. Right-hand behavior is positive, left-hand behavior is negative. I change signs, and I'm not defined for x less than 0. And I'm undefined at 0. I'm undefined for each of my roots of my denominator, and I'm 0 for e. Right-hand behavior is positive, left-hand behavior is negative. I change sign at 3 plus root 5 over 2. Right-hand behavior is positive, left-hand behavior is negative. I change at 3 minus root 5 over 2. I do my multiplication. I'm undefined for less than 0, undefined at 0, negative for less than 3 minus root 5 over 2, undefined there, positive, undefined, negative, 0, positive. And now I have a strict inequality. So as the inequality is strictly positive, x is in the interval 3 minus root 5 over 2 to 3 plus root 5 over 2, union with e to infinity. Now, like I was saying before, this question doesn't have the nicest numbers, but the process is the exact same. We use the split point technique. Factoring is hard. Okay, use the quadratic formula. The numerator has a root using lns. That's fine. But it's the same process. In B5, we have a function, not a polynomial. This is an exponential function. And we want to divide an interval n plus 1 such that f of c equals 0 for some c in that interval. When I see this, I'm looking at it and going, oh, this looks a lot like intermediate value theorem. And if we remember from before intermediate value theorem, we had to have a continuous function, and we had to have that the two endpoints bound the number we're looking for. So f is continuous everywhere. So we're good for continuous. So now we want two numbers such that one of our numbers is less than 0, one of our numbers is greater than 0. And then we can use intermediate value theorem. So I'm just going to start going with f of 0 equals 1.5 to the 0 minus 2, which equals 1 minus 2, which equals minus 1. F of 1 equals 1.5 to the 1 minus 2 equals 1.5 minus 2 equals minus 0.5. They're both negative, so I haven't bound 0. So let me check my next one. F of 2 equals 1.5 squared minus 2 equals 52705 add 5 2 2 2 decimals 2.25 minus 2, which equals 0.25. Yay! They're opposite signs. As f of 1 is less than 0, which is less than f2, and f is continuous over 1, 2, then by the intermediate value theorem, there exists a C in the interval 1, 2, such that f of C equals 0. Have to construct a graph with our specific constraints. So now I have a domain from minus infinity to minus 1, and I'm going to mark minus 1, and I'm going to mark 3, and I'm going to go, okay, from minus 1 to 3, that's where I'm defined. My range is the whole space, and I have an essential inequality. There's an essential, and I'm going to assume this is essential discontinuity at x equals minus 1. So what I'm going to do is I'm going to do this. I'm going to have an infinite discontinuity at minus 1 and go down to negative infinity over here so that I get that entire range. And now here, we're not including 3. So I'm going to do like a oscillatory discontinuity because it's kind of fun. And this is I'm going to put a little word oscillatory. And meaning it never actually hits a point. It never gets to 3. There's no definition at 3. And I'll put a little circle there to say, see, I'm not defined here. Lovely. And we have our B6. Now B7, it says, compute the following limits, provide appropriate justification. And what this is really saying is there will be a question asking you to solve a collection of limits. And I'll just have 4 limits. Can you solve?